chance of talking about this new work with Benjamin Bassot at ENS and Arthur Clemencius-Vero, which is a PhD student at ENS. I know this is not an integrability workshop, so we will try to be more pedagogical as possible. Some things, of course, this builds up on a lot of integrability, so it's going to be a very technical result, but I'll try to give some intuitive explanation of what we did, why this was a correct way to attack this problem, and more or less what are the possibilities to continue in this line of work. So there are different words in my title. One is hexagons, which I hope will be clear after I finish this talk, and the second one is short operators. So what one means by short operator is very easy to understand. So first of all, where we are in n equals 4 superunion mills, so we are in a 4D CFT. This is, has been studied for many, many years, especially in the planar limit, but the theory is supposed to be integrable. I mean, people now believe that the theory is integrable, and all the magic that happens is because the conformal symmetry and supersymmetry builds up to have like a huge symmetry group, which is PSV 2,2/4. Turns out that very many years ago, people also found that you can map trace of your operators to spin chains, and then you can try and understand all this picture of studying anomalous dimensions and structural constant or P coefficient in an integrability fashion. So what does this mean? It means that if I want to compute, for example, the anomalous dimension of one operator, I can in principle map it to the energy of a specific spin chain, and then I can extract this using integrability, so using different tools. And then I have practically, I'm able to compute this, the anomalous dimension of my operator. So this is a very naive picture. It works up to some loop level. Then people have developed a lot of new and fancy tools. And now, whenever one talks about n equals 4, always claims that the spectrum has been solved for single trace operators. And this is indeed true. Actually, it's very nice if any of you wants to dig into the integrability. There is a very nice paper by Volin and Marbeau that you can open. There is a Mathematica notebook, and in the Mathematica notebook, you can press Shift-Enter and get anomalous dimension for whatever operator, I think up to weight 8 that they have, but I think their approach is very general, up to 5, 6, 7, 8 loops. So it's really true that for the spectrum, we are able to control it in a very nice way. And also, we're able to do this at finite coupling as well. I've just seen from, I don't know, many of you were there, Friday talk by Zahara. So this two-point problem is very well under control, has been, let me say, solved. And the question is, okay, how can I approach, or how can I move to the three-point functions? Because then I would be able to really have all the data needed to have the theory under control. And as we've seen from Friday, there is some trying to do this in a non-perturbative way using Bootstrap. But there is also, of course, an integrability approach that builds on the fact that n equals 4 is integrable. Okay. So let me try and explain a bit what do I mean. So as we said, pictorially, one can imagine that if we want to compute some three-point function, we would care about 3 different operators. And then we can, of course, imagine them as some sort of, as I said, spin chain, so with some excitation representing some single trace operator. And then the idea is literally, okay, how can I, what can I do about these objects? Well, the tool that we want to use is this hexagons. So what are hexagons? Well, let me first dig into the fact that we cannot do much. So we cannot do 3 different operators which are non-BPS. The only thing that we can do is one non-BPS operator and 2 BPS. This simplifies a lot the constructions, and the idea is that also I will focus on a particular subset of non-BPS operators. Operators build up out of some scalar field Z and some derivative D. Okay, so this is the type of objects that I care about. I can build up single trace operator of how many z and how many d I care, and this PPS operator will be some trace of z's. Okay, in this picture,
sorry, this non-BPS operator at large lambda limit, they go to infinity or the
large length limit, I mean L. We will see what I mean by large L. So of course, let me just say. Sorry, can you repeat the question because I think I did not understand.
I'm saying in supergravity limits, this BPS they go to infinity or this non-BPS? They're scaling dimension.
Ah, the scaling dimension. No, I mean they're all single trace. The single trace. These ones are protected, so they will not change. This one will be some. Will not see it in supergravity. Will decouple. These are things that are purely string theory, so that's you cannot see them. This is also one of the problems because in supergravity you can see very well double trace operators, but you cannot. For now, studying integrability, so the two are a bit disconnected. But of course, since you have a DSCFT, you can also control this three-point function from coupling by studying it in some string theory setup, so you can have some idea on how it should behave as star coupling. Okay, very well. So the idea is that how can I map this to something that can be studying integrability? This has been done in 2015 by Pedro, Benjamin, Shota, and the idea was, okay, this object looks like this object cannot be studied as it is. Let me try and simplify it. And the simplification was literally trying and cut your three-point function into a combination of two fundamental building blocks that now are literally fundamental building blocks also for higher point functions. Explain a bit what I mean. Let me try and explain what I mean. The technique here is literally, okay, I want to understand how this behaves. Let me try and simplify it as much as possible. And by simplification, I really mean, let me construct an object that I can bootstrap by requiring some symmetry invariance, which is in this case not the full, which is connected to the fact that we have case of 2,2/4. And then let me try and reconstruct the full three-point function by gluing back this object together. And this cutting that was done is practically putting a resolution of the identity for some states. So the idea is now, okay, take whatever three-point function of this type, so BPS, BPS, non-BPS, cutting along the three different seams, construct these two objects, okay, and then try and reconstruct the full thing by gluing, and so by constructing, so by understanding how your maximum state will interact with this resolution of identity, so this infinite number of states and bound state. And this is what the hexagon is in its like simplest form. It's literally a way of constructing some amplitude, if you want, of so this object is known technically as loops. So this is, I can, if you give me whatever combination of marginals and states, I can construct this object, and then the idea is how do I glue it back, and this is the complicated bit. So gluing it back together is what it's cumbersome and has not been understood how to do it, and there was, so let me say this differently. So the gluing back together can be done, and as we will see, can be done easily for very large operators, because all these corrections, which are the state to plug in, are dumped to high loop orders. But if you want to study short operators, this cannot be easily done. As we will say, this will be connected to a problem that was also present in the spectrum, which is some finite volume effect. Practically, if your volume is not infinite, you can get particle creation that will be in some sort of way. You need to renormalize your non-BPS operator in such a way that to account for these finite volume effects. Okay, I hope this is somehow clear. Maybe not. Let me try and write this in a more explicit form. So what I'm trying to say is that whatever structural constant you want to compute with one non-BPS and two BPS can be written schematically, as I said, as a sum over all possible insertion of this resolution of identity particles. So normalization factor that, and then this will come with And then, as I argued, this is some square, which is related to this function. So, as I mentioned before, this is how you are, how you should think at the triplet function as canonical object dressed by this solution of entries that then I want to sum back. And of course, all of this will come with some weight, which is dependent on some length LB. And what is this length LB? Well, for whatever operator that I construct, I have some canonical weak contraction between the different edges. And of course, if I want to generate a particle, if I want to glue it together, the particle will need at least energy compared to how many lines it should cross. And this is what this is trying to do. So, what does it mean then to study this in the high length for long operators? Means that this bridges LB, LR, and L. So this is LB, LR, and LL will be very, 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 very long. And by being very, very long, we'll dump all the subsequent particle insertion that I want to study. And at the end, I will be, if I take them to be infinite, so if I study something which is all zeta to the L for L going to infinity, and this one is, for example, a 2 derivative with ZL going to infinity, this will give me that I just need to compute this hexagons with vacuum insertions, and that will give me my asymptotic treatment function. I don't know if this is over here. Very good. So, let me try and jump in and explain a bit better what happens if we don't study very long operators. So what happens if now I want to compute the Konishi structure constant. So now I care about something which goes to C2, and then I have trace of
Sorry, Alessandro, I have a question.
Yeah, sure.
So in that case, you are summing also the possible gravity contraction, right? I mean, these numbers L for the bridge lengths are can be different once you choose the three operators or not?
Yeah, I mean, you can practically, this L is constructed, for example, I think LB is contracted if you call this L1, L2. LB will be L1 plus L2 minus, let's call this of length L, minus L divided by 2. So this is the length. So LB can be whatever you want. There's 3 more cases where LB is 0, LB can be 1, 2, 3, whatever you prefer.
In this case, it seems fixed by the external states.
Yeah, it is. It is. This is the length of your external state. This is the classical weak contraction that you can do. Yeah. This is the least that you will need to cross the bridge.
Yes.
So the first correction. Yeah. Sorry. No.
I was wondering about if there was freedom in having more bridges from in one side and less in the other. But probably with 3 points it's not possible because it wouldn't match. The charges and
yeah.
the dimensions.
Yeah. I mean, you can solve it back in case of LB, LR, and L, and that will give you the same. It's 3 bar equals to 3 bar. Okay, very well. So now we want to focus on this, and the question is, okay, how can we do this? Well, as I mentioned, and I hope it is clear, the first step that you need to do is construct what is your asymptotic contribution, and the asymptotic contribution is the one without any particle in your capped edges. So distance will be in some pictorial way. We want one after we've glued it back together, exactly this. So I have a state, I've cut it, I've distributed my roots on all the possible hexagons, so this is a combinatorial problem, and then I just put it back together, arguing that there is this sum, it's trivial, I just need to care about the normalization factor. So I can do this, and this is my asymptotic contribution, and this is a correct representation up to, Konishi is the lowest operator, so this will work up to 2 loops. So up to 2 loops, we only care about this. Of course, this is the least for the Konishi. If you, as I mentioned before, if you add more LB and L, you can shift this to whatever loop you want, and in infinite limit, you can go to very, very high loops. Okay. So this is the first object that we care about. We know how to do this, perfectly fine. You can study it. Then the question comes, okay, what happens, what is the first excitation that I need to care about? And it turns out that the first that I need to care about is this bottom. I know I'm using different notations before, but please bear with me. So this is again, we want, let me do it in the same way that I did it there, otherwise this won't make any sense. Maybe, okay, this is it. This. Very well. So now we have one mirror magnet, and now the idea is that, okay, how can we do this? Well, first of all, for recognition, this, as I said, come into play at 3 loops. Okay. What do we need to do? Well, the idea is, again, you construct the hexagon from factor by starting it with one insertion of a mirror magnet here. You can shift it around to lines here. And then you try and see how your integrand, so how this H gets modified by the insertion of a mirror magnet. You can do this, this computation. It's not too complicated. And the idea is that this mirror magnet will interact with your excitation in the operator. So when I say excitation operator, I really mean that you can imagine it as some waves. So the operator will have different stationary waves, and then you call them different roots. This is complicated. Anyway, you can imagine how your mirror magnet will interact with your operator. Okay, and the idea is that then you can write some correction to the H bar integrand, and this will. Anyway, this will be integration over the rapidity, so the energy of your the rapidity of your magnet. Anyway, be clear. Most of you, let me try to finish. Give some explanation. Okay, say 1. That would be 1, and then. Okay. Sorry, maybe seem a bit cumbersome, but what I'm trying to convey here is that whenever I go over in this infinite cascade of particles that I need to insert, I can always correct my integrand in such a way to account for the interaction between this mirror magnet and my operator. And this comes into play in this object, which are practically conveying all the dynamics of this interaction. Why do I say this? Is because what we want to understand is what goes wrong when I go and I have finite volume correction. And the point that I will try to get to is that you need to correct this transfer matrix, or if you want this interacting term, to account for this finite volume effects. Okay. Let me go over to something wrong actually. This is 2 loops. This is up to 2 loops. Up to 2 loops. Okay, let me skip a bit since this is not very important. Let me go to the first case where we can have some interaction between. So skip a bit. Now the question is, what happens when I have then 2 mirror magnets on 2 adjacent edges next to the non-BPS operator? Well, this can in principle generate a pole and generate some divergence. So one would need to take into account how to deal with this kind of problems, and the idea one can think of is that, okay, well, what can I do? I know I have a pole in U equal V, so when the 2 rapidities of these 2 objects are the same, what can I do? Well, you can try and deform the contour. So say, okay, let me try and avoid to pick up this pole. This will not work. It will give you something that is not correct. But there is a way to do this. So first of all, let me try and convey some other message. Is the fact that one would argue, oh, well, why would you not have another? You can also have a magnet here that will give you the same sort of divergent effect. So what I mean is that if you look at this as a pole, so we'll V, this will dress up your two-point function with some wrapping effect. So the idea is that you cannot have them in here because the operators are protected, so this will not happen due to supersymmetry. Okay, so we have found, after doing this expansion, we found that we can go up to for loops, and for loops we start having problems. So if the operator is too short, so in this case Kanishi, we come into divergences. So what can we do? We can throw everything away, or we can try and understand how to fix these divergences. This has been done by Barstow, Shota, and that's it. Yeah. Anyway, various people, and what I will try to explain in very trivial and very pedagogical way is the fact that once you understand what object you need to change in your integrand construction, you can extend this correction to all possible effects, so possible wrapping effects. Because of course, the more loop I will go to, the more of this coincidence of Saramani I can have, the more wrapping I can go to, so I can go more. And of course, I need to understand how to deal with them because I cannot do it in a case by case. Okay. Let me cancel. Before I go into how to correct this, let me make some argument that if you keep on playing this game, you can see that actually you can write your two-hexagon contribution, so with whatever everywhere this. You can write this at some let's call it a weight for the left, weight for the right, and a weight for the bottom, where I have a multiplicity of these different weights. These different weights are practically this transfer matrices. So the idea is that this whatever I try to do factorizes, then I can construct these different weights for the different possible combinations. So if I have one of the left, one of the right, I can rewrite it as a transfer matrix. And then all this gets divided by some propagating factor, which tells me try and keep myself to make this really clear. We have some integrative construction on how to build building blocks for three-point functions. The idea, it's based on this gluing back together two hexagon for factors. I need to insert some mirror magnets that are gluing back together. I try to understand how this works for the different possible mirror magnets that I can insert. And the idea is that this will work, but has some problems with divergences and some it's a problem with divergences. But the idea is that I can in principle write some integrand, and then now I want to understand how to correct this integrand in such a way that it will work in the cases where I have wrapping effects or to higher loop orders. Okay, very well. So
Sorry, can you explain again why only for Konishi this happens?
No, it happens for all of them actually.
Okay.
Konishi is just the simpler, is like the one where it happens at the first, at the lowest loop level. So if you want to study a problem, you should start with the lowest operator. So this is kind of the most difficult thing you could try and think of.
So there's a relation between the length and the loop level where this...
Yes, yeah, sorry, I think it was not very clear, but this energy is LB and the energy of course will depend on the coupling. And so the more I expand, the more is big this, the more this will be dumped to a higher loop order. So yeah, this is the fact that, for example, as I said, this for Konishi happens at 2 loops. But actually, if I put more LB, which it's here, this will dump my factor to a higher and higher loop order. And so, yeah, one study Konishi because it's the one with the simplest one. So all the L's are equal to 1, so it's a simple case that one can attack. So I hope the picture is clear. We have some basic object and control integrability, we try and glue back, and then we find that there are some incongruencies on how you try to glue back things. So then we need to fix these incongruencies. And anyway, an idea, okay, let me try and focus on how we can solve this problem. But one can naively say, okay, let me try and understand what happens when I have this, which is my first rock introduction. Okay, what I can do is that I can construct some prescription through which I split this integral into 2 pieces, which is one piece shifted contours, so where I have avoided the fall by some plus I0 minus I0, prescription, plus some term which is fully localized, so it's some real contact term, and this fully localized term is the extra bit that you need to have some correct approach. So now the idea is that, okay, I can in principle do this. It's a very complicated and cumbersome computation. I need to understand how to write this. I can do it. So we're using this prescription. But as I mentioned before, you can do this order by order, which is not what you would like to do. So we'd like to find a way to recast your integrand in a Broppin completely resummed form. So what I want to write is I want to write weights that already by construction contains all the possible Broppin contributions. So you see, in this case, I had a divergence, and then by hand, I had to construct this localized term, this contact term. And then what happens is that this contact term looks very similar to your asymptotic contribution. So what you need to do is now you need to renormalize your asymptotic contribution. And the renormalized asymptotic contribution is the basic one, so the one with no excitation, plus the one with this Broppin collection. So the idea is this, So you try and figure it out how to play this game, which is, okay, I go to some loop order, I see what are my divergences, I try to regularize them, go start to encounter terms of shifting contours, and then I take whatever I get and I try to put it back in some weight that I know. And of course I can do this for all the bottom and multi-particle things, I just need to add the Bropping, and this will be my normalized version of this object.
Sorry.
Yeah.
Not sure I'm following. So you claim that we have this multiple sums and integrals
Yes.
with that kernel over there,
Yeah.
and you say that that integral over that kernel is divergent,
Yes.
and you need to have some prescription to regulate that integral.
Yeah.
Where does this prescription come from?
Yeah, so this is what I was trying to avoid, this is very technical. So the point is that what you can try and do is that you can try and do some, so for example, what you can do is that you can cut only along one seam, and then you can think of this as some two-point, for example, function, open, with some non-BPS insertions in the middle. So you can think of this as some sort of modification of a two-point function with an operator in the middle. And then you can take this limit for these things to be really, really large. And then you can try and see how this behaves. And then you can study this case by case by looking at all the possible insertion or mirror state that I can have. And then you can extract that this will, you can write this integral. It will depend on some y function, some complicated object which is not encoded in these asymptotics. So you can do it. It's very complicated and cumbersome. If you want, we can discuss this, but it's a very technical thing, which, if you agree what we've done, you don't need to do anymore because you already have the full thing. So you don't need to look at this in this way anymore, which is trying to see how the wrapping corrects and how to correct the integrand, because I mean, if what you've done is correct, you will have an integral which already contains everything. I think this is not being very clear, but let me try and be more specific and then see if I can answer your question. Okay. Okay. Very well. Now the question is how. Okay. Now the question is, okay, where has this wrapping effect already come into play? Well, when people were studying the spectrum, this was one of the problems that we had to deal with, and the tools that they used was this quantum spectral curve. So can we take building blocks from the quantum spectral curve and modify our integrand in such a way that will account for this wrapping effects? The answer is yes. Actually, what you can see is that, so the first thing you need to notice is that if I do this renormalization, so I recast all my contribution in this renormalized form, the factorization should also work. So I can also write something which is a new integrand, not this bare integrand, where I now have some addressed weights, which I call W a bit more dashed, and I can have a left and right one, and then I can also have the bottom. So this is E, this is left and right. Okay. Let me say what they are, and then hopefully it'll be clear. So, we have energy, state U, and then for the left or right, I can use some PhD objects, which are A1U divided by depending on what. Okay, let me try and explain a bit again. Goes to this and try to explain a bit why this is the correct. So, before I had these asymptotic transformators, now I've done this game of trying to write down this rapid correction in integral form, and I've argued that the integrand should stay the same, so I should have the same factorization in these three different weights. What I can do now is that I can dress up these weights by this infinite tower of rapid correction and try and understand what object will they lie to. Well, final answer is this, which is not very explicit to people who have not done quantum spectral computation, but it is that you can have some different transfer matrix, which is not that one, so different dynamics for your different weights, and this encode completely all the wrapping effects. So these different transfer matrix come from what is this quantum spectral curve, and they should be the canonical object they should have used from the beginning to describe your dynamics. So these are the fundamental building blocks of your theory. These contain all your conserved charges of everything, and they encode also all the possible of these possible corrections. So I know this is not very nice, but the only thing that I can try and say is that, yeah, is this.
Sorry, this is maximally cryptic. I have no idea what you're talking about.
Yeah, I know.
What do you mean it should have been and what we should have used?
Yeah, I know.
This type of words mean.
Yeah, I know. I'm sorry.
Confused.
Yeah, let me try. It's very complicated. Okay, for example, let me take the bottom. Okay, let me take this. You look at it and you're like, okay, why do you say that this is this transformators in this particular representation? Okay, the point is that if you look at this, let me try and run some tests to try and explain a bit better what happens here. Maybe very big. So what I want to do now is that I want to say this in the asymptote, in the weak coupling limit. Okay, so I try and expand this at weak coupling, and I move to a different sheet. So I move to this physical sheet. So I put everything back where the matrix are. And now you look at this for your A equal 1, and you look at how this look. Okay. And then you argue that you have two pieces for this object. Some bugs that are coming on like this. Very clear. let me just say this third. So you look at this object, you expand it with coupling, and you see that for this, which is not that, you get two different contributions. Now you try and understand, okay, why do I get two different contributions? I expect to have only one contribution, which should be some sort of the thing that I have in classical. So this bottom with one mirror, mark. The idea is that actually what happens is that you have an object which is the point is that this part will be exactly this contribution. So this will be some sort of first wave that contains this plus all your possible correction, which is what you would have expected canonically to be your bottom bit contribution. The second part actually contains an object that you can only see at 5 loops, which is this triple wrapping. And the triple wrapping is practically a second piece that you need to build your bottom integrand, is that you will not see it unless you go to very high order. Again, this is not very clear if you're not done in the. How can I better say this in different, in a less scripted way? Okay, let me try and say this differently. So your mirror minor should interact with your root. So this is what you want to construct this hexagon form factor. So how can I take into account the fact that I have a dropping correction or this sort of contribution is okay. I know that in the QSE I can construct an infinite tower of transfer matrices that clearly are the full thing, that contain all the possible dynamics, all the possible wrapping correction. So can I use these bases of object to describe my wrapping? The answer is yes. But for example, for the left and right, this is, you can do it directly. I think you could understand this way better. For the bottom, you cannot do it so easily because actually in doing the asymptotics, you miss a piece. So if you really want to understand how to reconstruct this in terms of QSE transfer matrices, you need to go up to 5 loops. Notice that there is an extra bit in there, which is a second wave with a different energy, with negative energy, so it's dumped to a very high order. And if you plug these two objects back together, then you get out that you need to use these transfer matrices. So there is a bit of turnaround, which is not very clear. But anyway, the main point that I wanted to convey is that QSE building blocks are the object that you should use to try and construct hexagons. And how you can do it, this is the minimal way in which you can do it. I understand it's a very cryptic result, not very clear, but I don't know, if somebody has some question, I can try and explain a bit better the direction that are not super clear. So my idea was, okay, let me try and explain how the wrapping come into play, how we can take account into the wrapping, and yeah, doing so by using some building blocks that automatically do it, but I don't know if that's such okay. Well, yeah.
Is this a conjecture based on trying to see? So you take the standard approach, you try to calculate the poles, and you start seeing that terms in the standard approach regroup and give it more compact representation.
Yeah,
this is how I should think? Or
yes, you should think it in this way. The point is that, as I was trying to convey, which is not good, for the bottom bridge, you can do this, but you will always miss a piece, which is this triple wrapping. This triple wrapping is physically like, in this sense, it's like a second wave, if you want, in your bottom bridge that you don't see. Because the idea is that, as I was trying to explain, is that you need to reconvey all this wrapping into whatever you had before, right? So this should be, the randomized version of this object should be a cascade of wrapping correction to this. But there is an effect, which is this triple wrapping that we computed with Flashco, that cannot be accounted for this. This is like a twofold contactor. This cannot be accounted in this way. You need to account for it as a different object, which is another piece, which then gives you a nice property of the bottom bridge that now doesn't have any pole on the physical ship. So now this is a well-behaved object. It says no pole on the physical ship, it has nothing. And the thing you can do then to test this minimal extension to the hexagon is try and see what can I match in perturbation theory or string theory. And this is what we have done. Practically, we have taken this conjecture, extract this transform matrices from the QSC, and then plug in the data and computed the integrals to see if we can match the perturbative data we had. And so, let me run. So the test that we tried to run was, for example, there is a quantity which I can write, which only depends on the bottom bridge, which is this. So I can construct a structure constant for state with, for example, LB equal 1 for Konishi, and then I can try and construct the same structure constant with LB going to infinity. All the adjacent part will factor out. I will get something that would only depend on the bottom contribution, right here. But anyway, I will get something that will only depend on the bottom contribution. Then I can use the QSC, compute WB to 5 loop orders, match it with the perturbative computation done with Feynman diagrams, and this works. So this is a not-trivial test of what we've tried to do. You can do the same at strong coupling, and you can see that this bottom bridge matches exactly the string theory prediction. So this is a minimal extension to the hexagon construction that seems to fit the data that we have available. Will this work to higher loops? Would this need to be modified? We don't know, but the structure seems to have the correct properties for it to hold even further test. Okay, let me try and conclude and then ask if there's any questions. So, what I hope to have conveyed is that we found a way to reincorporate all the wrapping corrections, all these finite volume effects, for the different weights of the hexagon in a very compact form, which relies only on this object coming from the quantum spectacle. So we've mixed two different approaches into one. And as I said, this seems to match perturbative data that we have, up to 5 loop orders, which before, if you could do, let me just say something else, if you would do this computation, you would get something which would miss exactly this wrapping correction. So this, if I compute this TA, which I can also write in a more compact form, so this TA1, it's QI, Q tilde I. Anyway, this can be written as fundamental Fermionic Q functions. So I can compute this object. I can extract this RLB, and this matches with perturbation theory. Before, I will not get these wrapping corrections, which would come from the correction, the correction coming from this object, plus the correction coming from this triple wrapping. So this, up to what we know, seems to be the correct formulation of these integrals. Of course, a lot of questions are there. Will this work for higher loop order? One will need to check against some perturbative computation. One will need to do more tests. Up to now, for what we have, this seems to be matching. The idea is that, okay, can we extend this computation to different sectors? So can we do fermions? Can we do anything else? Can we do more spinning operator? This is, of course, an open question. It would as well be that this bottom bridge will not be there, as this is like a very special case because we have, as I mentioned before, the two BPS operator don't get renormalized, so they are somehow protecting the bridge down there. So this is why this has a different form from the left to right. It would small b that if I have 3 non-BPS operator, the bottom bridge will be modified in a similar fashion to the left and right one. There is also another way in which one can try and approach this problem. Would be, okay, we have heard about the fishnet theory. Fishnet seems to be easier than n equal 4. Maybe there is some way using the QSC for the fishnet to construct this and maybe test it more extensively. So with this, I'm going to stop and let me just finalize by saying what I tried to start with. So what we've done is extend the hexagon formulation to short operator by constructing an integral that should account for all the possible wrapping correction that can be. our conjecture needs a lot of perturbative and non-perturbative results. So this is what it's more or less clear.
What would be the basic idea to try to derive these formulas?
I think what we've done, which I've conveyed under Rod, it's what I was trying to explain before. You can do this sort of like Leclerc-Mustardo approach to studying this two-point function. So as I was trying to say, you study a two-point function in this weird way. So you study it as there's B2 and then some BPS or non-BPS operator in the middle, right? And then you try and argue, how can I construct this object? Well, I can do it in an infinite volume limit, and I can try and see what happens, and I can try and use this Leclerc-Mustardo formula, and I get out, I can spit out practically this roughly corrected counterterms and everything that has been that I put it under the rug. Practically, how we've done is not guess what will be the QC thing. I was trying to give some more intuition of why we should do the correct form. Managed to. The real computation is this: you take your three-point function, you only cut along one seam, then you get a two-point function with some operator in the middle, and then you try to study this object in different limits, so infinite volume limit and small volume limit, and try and see if you can write this explicitly. You can. There is some way to. I think I'm not being really clear, but anyway, the idea is to study that, not what we've done. If you want to do it order by order. And
what is the operator in the middle?
The operator in the middle is the Kunishi, if you want, whatever you have, your excited, your Kunishi, non-BPS, whatever you want, if I remember correctly. Yeah, don't quote me on this. Actually, I need to check it back because it's been a long time. But
so the middle operator, you put an excited middle operator, which is Kunishi, and then vacuum on the bottom and top.
Well,
what's the second step?
Yeah, let me not. I don't know. I mean, I don't remember because it's been a long time, and I don't want to say wrong stuff. So we can discuss it later. But the idea would be to try, to construct this object from a purely integrability. Let me say this.
But what is this object?
Yeah, I don't know. I mean, it's complicated, and I cannot go into the details.
So up to what order has this OP coefficient been computed without integrability?
5 loops.
5 loops, yes. And with integrability, we've done it also to 5 loops, or can you go further than that?
Technically, one can try and go further. There are some complications that I've not mentioned for the left and right parts, which require some more combinatories. So this is a bit more complicated to study. But in principle, we've tested the contribution from this ratio, which is still, has interaction with this 5-loop result, and it matches with the integrability computation. I can push the integrability computation to a higher loop order and get some what would RL1 be at 6 loops, but then somebody would have to compute the 6-loop result perturbatively, which is currently not possible. So it's a bit of and what can achieve.
A more naive question. So this d squared, z squared is not quite the Konishi operator, it's an operator in the
It's the descendant, or it's one of the descendant, but you study because it's in the SL2 sector, and it's a bit easier to do integrability in this sector. But it's,
and some of the z's should be z bars?
Yeah, I think it should be z, so you can have z1 and z2, for example. I think that should be, should be z bars. Exactly. Yeah. This will.
Question? Are these T objects already a finite coupling object or just two elements?
No, finite coupling. Like you could. It's very complicated to do it because, like you see, finite coupling. It's numerical, but it's numerical in a different sense than one would expect. You can get this building blocks of this Q function that are open, and then you can construct these T's out of these Q functions. that usually you don't have the control of this Q function over the real line. You have this control over some specific points. So it's a bit cumbersome to do it. But in principle, if one gets better at numerics and understand how to solve a different problem, because when you try to solve for the spectrum, you don't really care of constructing this TA and T bars. They are just something that you have used to derive the QC, but all the information about the spectrum is in the asymptotics of this Q function. So you just need to know the asymptotics of this Q. Then, of course, this is a completely different problem, and you can solve it, as I said, numerically, but you never encounter these T's if you don't want. So in principle, what one can try and do is construct this bottom bridge at finite coupling, which is this RLB at finite coupling. Could be done, but maybe I did not mention this well enough. There is an infinite number of integrals. So this is the first, this is for one magnum. Of course, if I have multiple magnum in the bottom bridge, I need to have an infinite product of this integral. So of course, the full Risson object, so the full Risson hexagon, is an infinite product of this integral with this QSC T function. Okay, so it's still a very cumbersome, complicated object. But if you want, if you just want the leading approximation, so you just want one single integral, which just works up to 5 loops, then you would, for this P, you can just try and study how this would look. So this will be an approximation of the full object, but you maybe extract some finite coupling idea on how it should look.
Just very kind of naive general question. What is the expected form of this OP coefficient as you extrapolate from the weak coupling to the strong coupling qualitatively?
Nobody knows because, I mean, they add some graphs on Friday where they were showing how you can do some sort of matching.
I wasn't here last Friday.
Sorry, but nobody knows what it is. So there is some limit to infinity that should go to this string theory value, and then you know how it goes, how it increases.
But it should be like monotonic? Or
I think it should be monotonic, yes. So maybe there should be a pole when you mix with double trace, right? There should be
if you strip out some sign factor, and it should be monotonic. Okay. The sign factor incorporates the pole that you expect. Not refined much.
Should be when you mix with the double trace. So yeah, actually you could try and see this from this bottom bridge approach. So your W bottom should have also a pole. So practically, you should see that close to this, I think it's the coupling should be 0.55, but the dimension of the Konishi reaches almost 4. You should see that WB should have some exponential increase, and then the more integrals you plug in, the more they should be clear that at some point this will explode. So it's also an interesting thing to try and see if you could do QC mixing, but as I mentioned, the numerics are a bit cumbersome because you will need to compute this Q numerically on a very fine grid because you need to do an integration on top of it, so it's not as easy to get something nice. There's a couple of problems.
So as you go to infinite coupling, there's just infinite number of mixing.
Yeah, I think, I'm not an expert, but I think so. If you get one, then you cross it with some signs. I don't know, this thing with the double trace will be nice to see. It's just one needs to hammer it hard. I should also mention that also the left and right, because the left and right integral has some nice, I mean, there are some results, strong coupling coming from string theory, and they also match what we found. So if you take the strong coupling image of these D matrices, you can also see some nice structure that seems to also be there in the string theory.
Any further questions? If not, let's thank Alessandro.